Pulleys and wedges, type 1, 1 string, common tension, B, pulley. So in 1999 we were given 2 scale pans. So scale pan is something that is going to allow another mass to sit inside it. And we were told it's connected by a light inelastic string. So again, the fact that the string is inelastic is important because it means that the pans aren't going to be bouncing up and down. Now we're told it passes over a smooth, light fixed pulley. So again, this means that there's no friction between the string and the pulley. We then have a mass of 0.2 kilograms is placed on one pan and a mass of 0.4 kilograms is placed on the other. So that means that the total mass of the pan on the left is going to be 0.7 kilograms. So therefore the weight acting down is going to be mass times gravity, so 0.7 g. And the weight of the second pan is then going to be 0.4 plus 0.5, which is 0.9 kg. So therefore the weight would be 0.9 g. So again, mass times gravity. So we just remember that weight is equal to mass times gravity. So therefore we would expect the heavier one to accelerate down and the lighter one to accelerate up because they're connected by that common string, and because it's a common string they will have a common tension, and tension always acts away from the object. So in order to find the acceleration of the system, it's important that we realise that the system is released from rest, meaning that the initial velocity is 0. So of course, to work out our acceleration, we're going to set up our 2 equations and solve our simultaneous equations. And to do that, we're going to draw our force diagrams. So I'm going to look at the one on the left, first of all. In other words, the 0.7 kg part of the system. So if we draw our diagram, we have our scale pan, and we have the mass inside that scale pan. And then we have our tension acting away, and it's going to accelerate up, and the total weight acting down is 0.7 times g. So our net force in the vertical direction is going to be the difference between the tension and the weight. So of course, because I'm saying it's accelerating up, that means my leading force is going to be my tension, and the opposing force is going to be the weight. So the net force will be equal to the mass. So the net force will equal the mass times the acceleration. So of course the weight is 0.7 times g. The mass is 0.7 and times the acceleration. So therefore if I get t on its own, it's 0.7 g plus 0.7 a. So I'm going to call that equation 1. I'm now going to repeat that then for the second scale pan. So that's the 0.9 kg. So again, we have our scale pan. We have our mass sitting inside the scale pan. Our tension is acting away from the scale pan. The total weight is the combination of the scale pan and the particle sitting inside it, which is 0.9 times g. And it's the heavier of the two, so it's going to accelerate down. So again, the net force can be found in the vertical direction by looking at the difference between the tension and the weight. But this time, because it's accelerating down, my leading force will be the weight and the opposing force will be the tension. So therefore the weight is going to be 0.9 g minus the tension is equal to the mass, 0.9 times the acceleration. And if I rearrange that to get t on its own, that's going to be 0.9 a plus 0.9 g. No, sorry, 0.9 g minus 0.9 a. My apologies. So therefore that's equation 2. So now I have 2 equations in terms of t. So I'm going to equate 1 and 2. And by equating 1 and 2, I have 0.7 g plus 0.7 a is equal to 0.9 g minus 0.9 a. So by bringing all the a's to the left-hand side, that gives me 1.6 a, and all the g's to the right-hand side is 0.2 g. And therefore, if I divide across by 1.6, I get 0.2 divided by 1.6, which simplifies down to give me A is equal to G over 8. Now that's going to allow me then to find my tensions, but I don't need to find the tension in this question because I'm not asked for it. So I'd only need to find the tension if it's going to be relevant for the next part of the question. But the next part of the question is looking for the forces between the masses and the pan. So if I look at the forces between the masses and the pan, let's look at the 0.2 kilogram mass first of all. Okay, so the 0.2 kilogram mass is sitting on the scale pan. And therefore, because it's in contact with the scale pan, its weight is acting down on the scale pan, and therefore there is a reaction force with the scale pan and the mass. So I'm going to call that R1 because we have two pans, okay? And because it's accelerating in an upward direction, if I'm just focusing on the forces between the two pans, then the leading force is going to be the reaction force minus the weight equals the mass times the acceleration. Now, the weight is 0.2 g and the mass is 0.2 because, again, we're just focusing on the difference, the forces between the pan and the mass itself. And we've worked out the acceleration to be g over 8. So if I get R1 on its own, then it's going to be 0.2 g plus 0.2 g over 8. And therefore that gives me 9g over 40. Or if you're writing it in decimal, it's 0.225 times g. Now if we look at the second mass, the second mass was 0.4 kg. And it is in contact again with the scale pan. So again, we have the weight of the mass acting on the scale pan is 0.4 times g, and therefore there's a reaction force with the mass on the scale pan. Let's call this R2. This time it's accelerating down. So again, our net vertical forces will be the weight this time minus the reaction force is equal to mass times acceleration. And therefore the weight is 0.4 g minus R2 is equal to the mass, which is 0.4 times, again, acceleration is g over 8. And therefore R2 will be 0.4 g minus 0.4 g over 8. So R2 then simplifies down to 7g over 20, or 0.35 g. So in terms of marks, then we had 20 mark question. We had 5 for the first equation, 5 for the second equation, and 5 for solving for A, and then 5 for getting the two reaction forces. So again, another nice question.